Hello everyone. In today's session we are going to discuss about molecular orbital theory. This theory is obtained by linear combination of atomic orbitals. Atomic orbitals combine of which are of same energy, or I'll say comparable energy, to give rise to molecular orbitals, out of which we can say that half of the molecular orbitals are bonding molecular orbitals and rest half is anti-bonding molecular orbitals. The number of combining atomic orbitals is equal to the number of molecular orbitals that are formed. Now, the bonding molecular orbitals are obtained on account of constructive interference of waves. And in case of anti-bonding molecular orbital, they are obtained by destructive interference of wave functions. Wave, when I say, it is the wave function psi. That is the solution that is obtained from Schrodinger's wave equation. So let us understand in details and in a better manner. Hello everyone. So this is the molecular orbital theory, which says that in molecules, electrons are present in new orbitals which are known as molecular orbitals. They are the new set of orbitals in molecules where electrons can be present. Now, as atomic orbitals had the four set of quantum numbers characterizing the electron present in the atomic orbital, similarly, the molecular orbitals also are characterized by a set of quantum number. Now, molecular orbitals are formed by the linear combination of atomic orbitals. So, it is formed by linear combination of atomic orbitals. Okay. So now these combining atomic orbitals should have same energy, or they should have proper symmetry in order to combine. Now, nuclei of different atoms in the molecule, they behave as polycentric nucleus. What is the meaning of poly? That means many. Okay, more than one centered nucleus. So thus an atomic orbital can be what? Monocentric, and the molecular orbital is polycentric because it is containing obviously more than one atom. The number of molecular orbitals formed is always equal to the number of combining atomic orbitals. So if n number of atomic orbitals combine, it will give rise to n number of molecular orbital, out of which half of the molecular orbital, say n by 2, is having bonding symmetry, or they are bonding molecular orbital, and the rest n by 2 is anti-bonding molecular orbital. Now, what is bonding and what is anti-bonding molecular orbital? We are going to see. So we can see over here that the molecular orbitals that are obtained and which have energy lower, they are the bonding molecular orbitals, and the rest which have higher energy are the anti-bonding molecular orbital. Shapes of molecular orbitals, they depend on the shapes of the combining atomic orbitals. Next, the molecular orbitals are filled in increasing order. Just as we have seen in the atomic orbitals, electrons are filled as per energy. That is, lowest energy orbital is filled up first as per Aufbau principle. Same as over here. Okay, molecular orbitals are filled in increasing order of their energies. In Aufbau principle, we have seen that it was governed by n plus L rule. Okay, so which was having the atomic orbital which was having the lower energy was occupied first. Similarly, the molecular orbital having lower energy will be occupied first. Okay, molecular orbitals, like atomic orbitals, they can accommodate only 2 electron, that we have seen as per Pauli's principle, that they can accommodate only 2 electron. While filling degenerate molecular orbital, you have to keep in mind that pairing will not take place until and unless all are singly occupied. That is Hund's rule. So whatever was the rule for filling of electrons in atomic orbitals, it remains the same for molecular orbitals. Next, formation of the molecular orbital, I have said, it takes place as per linear combination of atomic orbitals. What is a linear combination? We need to see that. Now, the wave mechanics, as per wave mechanics, the atomic orbitals are expressed as wave function psi. Now, you have seen this wave function psi in Schrodinger's wave equation. Okay, you have seen this in Schrodinger's wave equation, where it was said that psi is the amplitude of the wave function, psi is the solution of the Schrodinger equation, wave equation, and all information regarding the electron is present in psi. Okay, so here let us see that when it is bonding scenario, what happens? When it is anti-bonding scenario, what is happening? For a bonding interaction, it says that two waves, they interact in a constructive manner. Two waves interact in a constructive manner. So it is known as constructive interference of two waves, for which I can say that it is a reinforced wave having a greater amplitude. So the amplitude of the wave function here, it gets added up. See, it is additive. These are the two waves which are in phase. What is the meaning of in phase? In phase means the crest of one aligns with the crest of the other. The trough of one aligns with the trough of the other. So the overlap that takes place is addition overlap for bonding molecular orbital. In contrary to it, for antibonding molecular orbital, two waves overlap in an antibonding manner, means the crest of one will align with the trough of the other. This is called antibonding wave interaction, which is a destructive interaction, which is a subtraction overlap taking place. This is the I will say reinforced wave for bonding molecular orbital, and this is a destructive interaction where the amplitude has got reduced on account of anti-bonding molecular interaction. So this is the representation for molecular orbital bonding and antibonding. Psi A molecular orbital, that is psi molecular orbital, is equal to psi A plus minus psi B. So if it is additive in nature, the wave functions or the amplitude of the wave equations, amplitude of the wave is additive in nature, psi A plus psi B will represent bonding molecular orbital having less energy. And in case of bonding overlap, the overlap takes place with orbitals having similar symmetry. So let us see how it is happening. Now for anti-bonding molecular orbital, the wave functions are subtractive in nature, or destructive interaction takes place, destructive interference of waves takes place, and this is known as a subtraction overlap. And let us see the combination of 1s orbital forming hydrogen atom. So that is also a molecular orbital, because two hydrogen atoms are combining to give a molecule, that is H2, and 1s1 configuration hydrogen has. So what is the interaction? Let us see here. In this diagram, the relative energy of bonding and antibonding molecular orbitals are shown. So this is the atomic orbital of hydrogen. This is again the atomic orbital of hydrogen. Now here there is one electron, here there is another electron. 1s1 configuration, we know it is for hydrogen. So how many atomic orbitals we can see? 1 plus 1, that is 2. This is finally, this is 1 and the other one is 2. Similarly, I have 2 molecular orbitals formed, out of which one is bonding molecular orbital and the other is anti-bonding molecular orbital. So this is anti-bonding molecular orbital, or simply I can say AMO, that represents anti-bonding molecular orbital. So anti-bonding molecular orbital is energetically higher, we can see, and bonding molecular orbital is energetically lower. And 2 electrons are there, 1s1 configuration. Both the electrons are oriented in sigma 1s orbital, molecular orbital, and the anti-bonding is vacant because there are only 2 electrons present in this molecular orbital. Now, the probability density of the bonding molecular orbital is given by psi b square. We know psi square is the probability. So psi b square is the probability density of the bonding molecular orbital. And if the bonding molecular orbital is equal to psi a plus psi b, the square of it will be the probability density. Next, for this, we can see that addition combination leads to increase in electron density between the 2 nuclei A and B. How is it? Let us see. If I say this is the wave function for hydrogen A and this is the wave function for hydrogen B, and here addition is taking place, means psi A plus psi B interaction is taking place. For that, the probability density has increased at the center. And that is the reason the nucleus moves at the 2 end and the probability density is greater at the center of the combining molecular orbital. So the experience, in other words, we can say that electron present in bonding molecular orbital, they experience greater force of attraction, thereby lowering the energy. See, we have seen in VBT that when 2 atoms, they approach each other in order to form a molecule, what happens is there are 2 types of interaction, attractive as well as repulsive. Bonding scenario mein kya hota hai? There is a lowering of the energy because of the attractive interaction that actually supersedes, rather, I will say. Now, the probability density of the anti-bonding molecular orbital, that is psi a square, and since anti-bonding molecular orbital has a subtractive interaction, so psi a minus psi b whole square, that will be represented by the probability density. So subtraction combination leads to lowering of electron density in between the nuclei, for which what happens, the electron density, in fact, what happens, it is concentrated away from the nuclei, creating a node. What is a node? Node is where the probability of finding an electron is almost nil. Okay, now the electrons present in the anti-bonding molecular orbital, there the repulsive interaction will be greater, for which there occurs a raising of energy, because repulsive interaction is not a stabilizing interaction, and wherever there is destabilization, there is increase in energy. So this is what is happening, psi a minus psi b, subtractive interaction for anti-bonding scenario, and this is your node where the probability of finding the electron is almost not there. And so the shape of the anti-bonding molecular orbital for a sigma overlap is like this. Okay. So next we have already discussed about the diagram where the energy order of forming the molecular orbital of H2 is being depicted. When you are drawing the molecular orbital, certain rules are there which you need to follow. First is write the atomic orbitals on both the sides. Maintain a symmetry in your diagram. In between, draw the molecular orbitals, and this is your barycenter, where you can actually, with reference to this energy level, you will show how much stabilization or lowering has taken place, how much destabilization or raising of energy has taken place for anti-bonding and stabilization for bonding. And this energy has to be shown. I mean, it needs to be shown. This is the energy order, where if you don't show this, then you actually cannot show that, okay, bonding molecular orbital is having a lower energy than the anti-bonding. It may be noted that energy of anti-bonding orbital is raised above the energy of the atomic orbitals. What is the energy of the atomic orbitals? This is the energy of the atomic orbitals, which I am telling as the barycenter. The comparison, of the raising or lowering will be as per the with reference to the barycenter, I can say. Okay, so in other words, destabilization effect of atomic anti-bonding molecular orbital is more pronounced than the stabilization effect of bonding molecular orbital we are seeing here. So here what is happening? See, in case of formation of molecular orbital, I have told you one thing, that the combining atomic orbital, number of combining atomic orbital is equal to the number of molecular orbitals obtained, and half of it is antibonding and half of it is bonding. Antibonding is raised in energy, bonding is lowered in energy. But I did not say that as much lowering will take place, that much raising will take place. So in the formation of hydrogen, lowering is not that much pronounced as the raising. Okay. So now bonding molecular orbital and anti-bonding molecular orbital, what is the difference? The first difference is addition overlap that takes place of atomic orbitals for bonding molecular orbital, subtraction overlap taking place between atomic orbitals for the formation of antibonding molecular orbital. Next, you can say that the energy is less than the energy of the atomic orbitals and energy is greater. That means bonding molecular orbital have a lowering of energy, antibonding molecular orbital have a raising of energy. Bonding molecular orbital may or may not have a node, but anti-bonding will always have a node, okay, between the nuclei of the bonded atom. These are the three most important ones. And the other one where I am telling that there occurs a lowering of the energy of the atomic orbitals for bonding molecular orbital. Here, obviously, I want to say that the attractive interaction is actually more powerful. It supersedes the repulsive interaction. But for anti-bonding, the repulsive interaction supersedes. Okay. So next, let us see conditions for the combination of atomic orbital. What are the combinations? Linear combination of atomic orbital have certain condition. So the first condition of combination of atomic orbital, that is linear combination of atomic orbital, is what? The combining atomic orbitals should have almost same energy that we have seen. So 1s orbital of one atom can combine with 1s only. But 1s orbital of one atom cannot combine with the 2s, that we have already understood, I suppose. Atomic orbitals participating in combination must overlap to the maximum extent. Combination, if it is combining in order to form molecular orbital, then the extent of combination will decide the density, the probability density of the electron. Greater the extent of overlap, greater will be the electron density. Combining atomic orbitals should have same symmetry about the molecular axis. Okay, like if I say 2px orbital of one atom, it can combine with 2px orbital of the other atom, but not with 2py or 2pz. So these things need to be understood. One thing with reference to which we always draw the molecular orbital or the atomic orbital, that z-axis is taken as the internuclear axis according to the modern convention. We know that x, y, z, they are three mutually perpendicular axes, and orientation of the p orbital along the axis will define it to be px, py, pz. But keep in mind that there is a convention, a common convention, where z-axis is taken as the internuclear axis. Next, types of molecular orbitals. In the hydrogen bond formation, there is a sigma, in the molecule of hydrogen H2, there we have seen a sigma overlap taking place. So this can be a sigma, can be pi, can be delta, but right now we are not going to talk about delta overlap. We will be talking about sigma and pi molecular orbitals. The molecular orbitals which are cylindrically symmetrical around the internuclear axis or bond axis, they are the sigma molecular orbital. Or in a simple manner, the atomic orbitals that combine almost in a head-on manner, that is the sigma overlap. So here we can see the sigma molecular orbital formation. This one is a bonding, the other one is anti-bonding. This is bonding molecular orbital and this is anti-bonding molecular orbital overlap and formation of course, sigma. This is it. Next, if I talk about P, because S will always form a sigma overlap. This concept, I think we are clear with it. But for P, we have three different axes, three different directions or orientations, Px, Py, Pz. So here what is happening? 2p orbital, as the 2pz, we are taking an example, okay. So 2pz orbital is assumed to lie along internuclear axis. So we are assuming that molecular orbital formed by the addition overlap of 2pz is a sigma 2pz as per convention. The 2pz is oriented along the internuclear axis, and if head-on overlap is to be occurring in order to produce a sigma molecular orbital, it will be of the 2pz and it is named as sigma 2pz, while the molecular orbital formed by the subtraction overlap is what? 2pz overlap will be sigma star 2pz. So this sigma 2pz is what? It is bonding molecular orbital. And to show the subtraction overlap of this same 2pz is a sigma star 2pz. That is the anti-bonding molecular orbital. Anti-bonding molecular orbital of higher energy is shown by a star. Okay, so this is how you are showing 2pz and 2pz. See, it is addition overlap, and here the plus sign is increasing. This is the plus sign and this is the minus sign. So same symmetry overlap with same symmetry, and the negative symmetry, the other lobe is like this. So how this is taking place? If I say this is one 2pz with a positive sign in one lobe, the negative sign in the other. Another 2pz has a positive sign here and negative sign here. So the positive symmetry, the area under the positive lobe after overlap increases. Now for anti-bonding, it is a subtraction overlap where the area should decrease. An anti-bonding orbital will look somewhat like this. It will look, and this is the nodal plane. This is the node, and the symmetry will be opposite. If this is plus, the other one will be minus. So this is minus, this will be plus. So you always observe the symmetry in order to understand whether you are going to represent a bonding or anti-bonding molecular orbital. Next, pi overlap, that was a sigma overlap head-on. Lateral overlap of p orbitals, that will give rise to pi molecular orbital. Remember that they are not cylindrically symmetrical around the internuclear axis or bond axis. Let us see. Now 2px orbital, if it undergoes overlap, it will form a pi 2px, which is a bonding molecular orbital, and it will form a pi star 2px, which is is anti-bonding molecular orbital. How do we show? See, this is the 2px. So if I say this is plus, this is minus. Addition, overlap. So again, this will be plus, this will be minus. So remember, this is the nuclear plane, no? So the bonding picture, the pi molecular orbital will be somewhat like this. Here it is a plus sign and here it is a minus sign. It is like this. And there is a nodal plane you can see. For anti-bonding pi molecular orbital, it will be a subtraction overlap. And what will happen? There will be repulsive interaction. No. So the lobes you can see, they are almost repulsing. They are repulsing as if they are repulsing from each other. Since it is anti-bonding, if you make a plus here, you have to make a negative symmetry here in order to show the opposite symmetry for anti-bonding molecular orbital. Now the energy level diagram for molecular orbitals, this is very, very important. We need to know how to draw the energy level diagram, how to write the molecular orbitals. Okay, so here we can see that 8 atomic orbitals of 2 atoms here. It is giving rise to 8 molecular orbitals, and so these are the molecular orbitals sigma 2s. So sigma star 2s, correspondingly it is having bonding, anti-bonding, pi bonding, pi anti-bonding. Okay, so here again pi bonding, pi anti-bonding, and here sigma. So why you may think that, ma'am, here there is a sigma bond formation, next there is a pi bond formation, and again there is a sigma bond formation. This is as per the energy order of the molecular orbitals obtained, and the increasing order of the energies of various molecular orbitals are like this. But the molecular orbital energy diagram, this is for oxygen or F2O2, F2Ne2. That means what? They are having greater than 14 electrons in total. Oxygen has greater than 14 electrons. So there are 2 types of molecular orbitals. One is the one having 14 and less than 14 electrons in their molecular orbitals, and the other is that having greater than 14 electron. The order is like this. You may actually focus on the variations that take place here. The variations are what? Here you can see that after sigma to star 2s, and there comes sigma 2pz, and there is pi 2px equal to pi 2py, same energy, less than, it is anti-bonding of it, and then you have sigma star 2pz. This is the difference between the 2 types of molecular orbital. I would like to show you the comparison. Here just see the position of this sigma 2pz. Okay, and now moving on to the 14 electron and less than that. Here you see sigma 2pz. What is the position? It is after the pi 2px equal to pi 2py. So this is only the variation that occurs where you draw the molecular orbital or mention the energy order of the molecular orbitals of molecules containing either 14 or less than 14 electron, or greater than 14 electron. This is greater than 14 electron. So I can say that this is the difference which you are seeing. This is the difference which you are seeing, that sigma 2pz is less than pi 2px equal to pi 2py for less than 14 electron, and for greater than 14 for greater than 14 electron it is this. For greater than 14 electron it is this. For less than 14 electron or 14 electron, there is a swap over here. There is a swap. Okay. So let us see O2, F2, Ne2. Question arises that why does Ne2 molecule not exist? Okay, so for that we need to find the bond order. You know what is bond order? Bond order is how many bonds are existing between the atoms that are forming the molecule. So let us see what is bond order. Bond order is number of bonding molecular orbital minus the antibonding molecular orbital by 2. Okay, bonding electrons. So let us see how many electrons are there in bonding, how many electrons are there in antibonding. You subtract it, divided by 2. Let us see that. Okay, so let us compare. This is of O2 and F2. Electrons are not filled. Okay, you just need to fill the electrons. This is the energy order. You need to practice the energy diagram very nicely, understanding it. Whether you give a circle or you give a box like this, doesn't matter, but make it correct. Okay, so here we can see atomic number of oxygen. So O2 will have 16 electrons. So what is it for O2 case? Suppose I say I want to show O2. So it will be atomic number 8. So 1s2, 2s2, there is 4, then 5, 6, 7, 8. This is it. So it is 1s2, 2s2, 2p4 configuration. Okay. So both the sides I need to show that 1s2, 2s2 and 2p4 configuration for oxygen atom. So there I will show this is oxygen, this is also oxygen atomic orbital, and this is O2 molecular orbital, where I will have to first draw the molecular orbitals as per the knowledge that we have gained, that if it is greater than 14 electron, then it is sigma 1s, sigma star 1s. That is sigma 1s less than sigma star 1s, then comes sigma 2s. So you always remember that when you are drawing sigma 1s, you consider this as the barycenter and you make the bonding and antibonding orbitals. Okay, now here again you make the bonding and antibonding orbitals, and for P only you need to be very careful. There is one below, that is your sigma 2pz. Now pi 2px is equal to pi 2py was said, so they are having same energy. They are degenerate molecular orbital. This too is also degenerate molecular orbital. Okay, so this is also degenerate molecular orbital, and then this is the antibonding. Last we can see sigma star 2pz. In both the case we can see sigma star 2pz. The only thing that varies is this part. This part is different in both the diagrams. So if I say that I am going to show O2 which is having 16 electrons, then I will write sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. So 1, 2, 3, 4, 8. Now this is again having 9, 10, 11, 12, 13, 14, 15 and 16, like this. When I filled up the degenerate molecular orbital, I hope you noticed that first I filled both the degenerate molecular orbital with single electron and then I paired up. So first it will be singly occupied, then there will be pairing of electrons. Now in case of N2, or I will say in case of molecules containing 14 electrons, or less than that. Okay, so we can say 14 electrons or less. For that, this is the molecular orbital diagram, and accordingly we can fill up the electrons the way I have shown for O2. So this is it. that is saying that why energy levels of molecular orbitals of B2, C2 and N2 are different from O2. This is the explanation. Okay. And what is the explanation? That the orbital interaction is important over here. Okay. Now in case of B, in case of C and in case of N, the difference in the energies of 2s and 2p levels are quite small, for which there is, when they are coming close, that is due to close proximity of these energy levels 2s and 2p, there occurs mixing of interaction. So mixing interactions occur and the energy order gets reversed. Okay. So now over here, this causes the energy of sigma 2pz orbital to be raised. Because what is happening? It becomes greater than this because the pi orbitals, they are having more stability than the antibonding at that time. Okay. So electronic configuration and stability. Now number, if you have to see whether a particular ion or a particular molecule is stable or not, there are certain things which judges the stability of molecule. The molecule is stable if, what is it? If the number of bonding electron is greater than the number of antibonding electron. For that only the bond order will be positive, no? So bond order is what? I said number of bonding electron minus number of antibonding electron by 2. If bonding is greater than antibonding, then only the bond order will be positive and the molecule will be stable. And the molecule is unstable if the reverse takes place or if it is equal to. In those cases, it can be 0 or negative. So in that case, the bond order will also be affected and the stability of the molecule will also be affected. Destabilizing effect of antibonding electrons is slightly more than stabilizing effect of bonding electron. So even if number of electrons in bonding molecular orbital and number of electrons in antibonding molecular orbital are equal, the atoms do not combine to form molecule. We have seen the antibonding getting slightly more raised than the bonding getting lowered, right? So that is the reason. Bond order is what? Number of bonding minus number of antibonding electron divided by 2. How does it affect the stability? Let us see. The molecular stability, I have already said that bond order is a parameter that shows molecular stability. If it is positive, then it indicates a stable molecule. If it is negative or 0, it indicates unstable and that molecule does not exist. The bond dissociation energy depends on the bond order. If the bond order is high, greater the bond order, the bond dissociation enthalpy or the bond enthalpy is also greater. Greater the bond order, greater the bond order, more number of bonds exist between the atoms and the bond length decrease. Okay, it is decreased. So bond order is related to bond enthalpy. Bond order is also related to the bond length. Bond order means how many bonds exist between the atoms that are forming the molecules, and you can mathematically calculate bond order by number of bonding electrons minus number of antibonding by 2. If the bond order is greater, that means the bond is stronger, the bond enthalpy increases, and if the bond order is greater, the bond length decreases. Shorter will be the bond length if the bond order is greater. Now, number of covalent bonds, again, if you know the bond order, number of covalent bonds between the atoms and the molecules can be predicted. Okay, so bond order of a molecule is equal to the number of covalent bonds between the atoms in the molecule. If anyone is asking you how many covalent bonds will be formed, you can find the bond order and then you can relate it that as many, whatever is the bond order, that many covalent bonds will be formed. Now, this magnetic behavior is also judged seeing the molecular orbital. How we have magnetic behavior like paramagnetic, diamagnetic behavior. Electrons are charged species, so they are supposed to have magnetic behavior. Now, diamagnetic substance means the electrons in the molecules are all paired up. If there is even one unpaired electron in the molecule, then the substance is paramagnetic in nature. Remember that a diamagnetic substance is repelled by magnetic field and a paramagnetic substance is attracted by a magnetic field. And how to see whether it is a paramagnetic or diamagnetic? Simply see whether there is any unpaired electron or not. If there is even one unpaired electron, then the substance is paramagnetic, and if the substance is paramagnetic, it is attracted by magnetic field. And if you have all paired electron, then what will happen? The substance is diamagnetic, and since it is diamagnetic, it is repelled by magnetic field. Now, the magnetic character, the magnetic moment is measured or calculated by this formula, root over of n into n plus 2 Bohr magneton. N is how many unpaired electron exist. So, what all things you are seeing over here? You are seeing over here how to draw the molecular orbital, how to write the energy order of the molecular orbital, what happens to the energy of the molecular orbitals for molecules containing 14 or less number of electrons and molecules containing greater than 14 electrons, how you can find the bond order and how you can relate it to the stability of the molecule, how you can judge the magnetic behavior, paramagnetic or diamagnetic, and how you can measure the magnetic moment. That's all for this session. See you in the next session. Thank you, all of you.